Hello, in this video we study infinite limits. We learn how to determine infinite limits and understand the geometrical meaning of such limits. Actually, we already saw some problems like that in the past, but today we will discuss more examples. Let's remind you the one we discussed in the very first lecture. The function 1 over x. And this function is not defined as 0, and we know that the function does not have limit as 0, right? Because the left limit and the right limit are different. The left limit of this function is limit of 1 over x when x approaches 0 from the left, means x less than 0, right? And this is negative infinity. And the right limit is limit of 1 over x when x approaches 0 from the right. That means x greater than 0, and this is positive infinity. You see, they are different. So from here, the function does not have limit. This limit does not exist. But what does it mean? Positive infinity and negative infinity. I think we already sketched the graph of this function, right? But let's repeat that again. X in here, 0, and y in here. So you may give a sequence of values, right? I have x right here, and then 1 over x in here. So we may write 0, 1, 2, 3, or negative 1, negative 2, negative 3. So you have negative 1/3, negative 1/2, negative 1, 0. The function is not defined. You have 1, 1/2, and 1/3. So basically, the graph of function has two parts, and they are symmetric with respect to the origin. You see, they are symmetric. Negative 1, 1, negative 1/2, 1/2, and then if you consider 3 and 3, and so on. They are symmetric with respect to the origin. Now let's express them on the x or y plane. So let's say this is 1, this is 2, this is 3, this is negative 1, negative 2, and this is negative 3. Okay, so if that is 1, we have 1. If 2, so we have 1/2. If 3, we have 1/3, right? So we have 3 points in here. We can connect them. So we get what we need, right? And then the other one looks like this. 2 is negative 1/2, and 3 is negative 1/3. So I will connect them. I get this part. So you can see, actually, the graph of function, right, approach to positive infinity, right, when x approaches 0 from the right. And this part will approach negative infinity when x approaches 0 from the left, right? And in this situation, x equal to 0. This is the vertical line, and that is the y-axis, right? This axis is called the asymptote, right, of the function. So we know about this already, right? But this is the first time we talking about asymptote of a function. Okay. In this situation, the function does not have limit at 0, but the left limit or the right limit exists and equal to infinity. In that case, that straight line, that vertical straight line, is called asymptote of the function. Okay, so I can summarize. If you have some function f of x, and the limit of f of x goes to a plus or x goes to a minus or x goes to a, right? This okay. Equal to positive infinity or negative infinity. Then x equal to a is vertical asymptote of the graph of f of x. So this is the definition of vertical asymptote. That means in order to find vertical asymptotes, we need to find points where the function has limit or one side limit equal to infinity, right? And of course, such points should be found from where? From the denominator. So if your function does not have the form like f of x divided by g of x, there's no way, right? But you may find such point by putting g of x equal to 0. That's what we did right here. We put x equal to 0. Let's consider another example. Let's find our vertical asymptotes of the graph of this function, x squared plus 1 over x squared minus 1. So this function has the form f of x over g of x, right? In order to find our x that can be vertical asymptotes, we need to solve gx equal to 0, or in this case x squared minus 1 equal to 0. Okay, so you have x minus 1 times x plus 1 equal to 0. From here you get x minus 1 equal to 0 or x plus 1 equal to 0. Then x equal to 1 or x equal to negative 1. So we have two candidates. Okay, two candidates. They are still not vertical asymptotes. We need to verify that. But in order to find all candidates, we need to solve the equation gx equal to 0. We need to find, just put the denominator equal to 0 because we cannot divide by 0. And only in that case, we might have infinite limits. Okay, so what is the next step? I need to consider each point here. Let's say at x equal to 1. So at x equal to 1, I need to consider the limit, okay? Because limit, if the limit is not infinity, so we don't have vertical asymptotes. I have limit of x squared plus 1, x squared minus 1, x goes to 1. So how do you think about this? The limit of this is x squared plus 1 over x minus 1, x plus 1 when x approaches 1. We consider a very similar problem like this. You see, when you plug 1 into the function, what do you get? You get 2 over 0, right? So we might think about this. At x equal to 1, x squared plus 1 is similar to 1 plus 1 is 2. Okay, I have x plus 1 is similar to 1 plus 1 is also 2. So my function x squared plus 1 over x minus 1, x plus 1 is similar to 2 over x minus 1 times 2, which is 1 over x minus 1. Okay, of course, if you can just consider the left limit and the right limit, you see, infinite right way. But I try to avoid that because, maybe it's a long way, okay? But here's the thing. If you plug the number, right, into the function, you see, yeah, you got some number, that's fine. Whatever you get, you just keep that. In here, I have 2. In here, I have 2, which is good. We don't have any, special information. at 0 for such terms, right? We only need to consider this term. So, by the way, the function 1 over x does not have limit at 0. We just discussed about it. Then, if you shift, right? If you move this function to the right on 1 unit, okay, so this function does not have limit at 1, right? And of course, you may obtain this function from this guy by moving the graph of this guy to the right on 1 unit. So in this case, the function 1 over x minus 1 has a vertical asymptote x equal to 1. It is similar to the case of 1 over x. Okay, so from here I can write conclusion. Yes, x equal to 1 is vertical asymptote. Because the limit of this function at 1 from the left or from the right equal to infinity. And so this function also has infinite left limit or the right limit, given that the function does not have limit at 1. Okay. Similarly, we can consider the point, at x equal to -1. You do almost the same thing, but at -1, so you get x squared plus 1 over x minus 1, x plus 1. That is similar to 1 plus 1 over -1 minus 1, x plus 1. And this is -1 over x. Again, right? The difference is only in the sign. So I can do conclusion right away. X equal to -1 is vertical asymptote. That means the function has two vertical asymptotes. X equal to plus minus 1. Alright, so the solution of this problem has two parts. The first part, we need to find all candidates that may be vertical asymptotes. The second step, we need to check each of them. You see, we need to check if the limit or one side limit equal to infinity or not. Okay, and we just reduce the case to the well-known case 1 over x. Right? I mean, in the very first lecture, I remind you, I told you that 1 over x is very important function, so we will use that all the time. And this is just one case of that. Agree? In the following example, we see actually when you have the function of the form f of x over g of x, and when you finish the first step, I mean you solve this equation, you can find all candidates, but not every candidate will be vertical asymptote for the graph. Okay, so again we need to put g of x equal to 0. That means, let me write in here, we need to solve x squared minus 4 equal to 0, and you have x minus 2 times x plus 2 equal to 0. Okay, you have x equal to 2 or x equal to -2. I just put each of these factors equal to 0 and solve for the x. All right, so we have 2 points, right? 2 candidates. Now let's check at x equal to 2. What happened? We need to find the limit, right? We need to evaluate the limit. X squared plus 2x minus 8 over x squared minus 4. X approaches 2. Now you just plug 2 into the function. What do you get? When you plug 2 into the function, you get 2 squared plus 2 times 2 minus 8 over 2 squared minus 4. And you got 0 over 0. What does it mean? That means 2 is common factor, right? So we need to factor the top and the bottom by x minus 2. And then we simplify this term, okay? Let's do that. I have, this is limit of what? On the top, I have x minus 2. So I have x squared, means here I need x. I have negative 8 in here, but here I have negative 2. That means I have 4, right? So I got x plus 4. X approaches 2. We already know this is x minus 2 times x plus 2. And we simplify x minus 2 in here. We got limit of x plus 4 over x plus 2. X approaches 2. And then you plug 2 into the function. You got 2 plus 4 over 2 plus 2. This is a finite number, which is good. That means the limit is x and equal to a finite number. That is not infinity. You see, this limit is not infinity. By the definition, this is not a vertical asymptote, right? So from here, I can make conclusion, x equal to 2 is not a vertical asymptote. You see, not every candidate will be vertical asymptote. Okay, then the next is at x equal to negative 2. You do almost the same thing, right? You need to consider the limit of x squared plus 2x minus 8 over x squared minus 4 when x approaches negative 2. And again, you plug negative 2 into the function. You got 4 minus 8 over 0. So that is about, negative 8 over 0. It seems like the function has a vertical asymptote at this point, right? So how to write a solution? I will accept the following solution. You can write at negative 2, x squared plus 2x minus 8 over x squared minus 4 is similar to what? Is similar to negative 8 over, again you factor x minus 2 in here and x plus 2. And you plug, negative 2 into this. So this is negative 8 over negative 4 times x plus 2, which is 2 over x plus 2. And we know exactly that at negative 2, this function does not have limit, like 1 over x, right? But this guy is at 0. So, and the limit, but the one-side limit of this function is negative infinity if x approaches negative 2 from the left, and positive infinity if x approaches 2 from the right. So this limit does not exist, but one-side limit exists, right? The limit does not exist. I write here. But one-side limit are infinity. So x equal to negative 2 is a vertical asymptote. You see, we have two candidates, but only one is vertical asymptote. So what is the difference between them? Look at this. The difference between them is the point x equal to 2, in this case, is the point of discontinuity, and this is removable discontinuity. I hope you still remember that, right? Removable means the function is not continuous at that point, but the limit exists and equal to a finite number. Equal to a finite number. Unremovable discontinuity is the limit does not exist and equal to infinity. Right? So, if that is the point of unremovable discontinuity, so you have vertical asymptote. If that is removable discontinuity, you don't have vertical asymptote. Don't forget that. So let me summarizing this. If you have removable this, let's say when x equal to c, right? You have removable discontinuity, so that is not vertical asymptote. But if that is unremovable discontinuity, so you have vertical asymptote. You see, it's very interesting, right? And actually, if you have infinite limit, so we know that the behavior of function here may be very strange, right? Like this. Like this. Infinite limit. But if you don't have infinite limit, so you might have the following case. That is removable discontinuity. You see? And this is unremovable discontinuity. All right? Okay, so I hope that you enjoyed the video. And if you have any questions, please feel free to let me know. Thank you.